In this lecture, we're going to discuss the moment of inertia for a rotating rigid object. So, first of all, it's important to realize that this is a big assumption that I'm making, that it's a rigid object. A rigid object in physics is one that's considered to be non-deformable. And what that means is that if you find the center of mass of the object, that all the little particles that make up the object with respect to the center of mass stay in the same position. Now, it's true that real objects are deformable to a certain extent, but the rigid object model works really well for some lots of solid objects where it doesn't deform very much. Bear in mind that this is a simplification, and so if you have an object that has, for example, a liquid or some kind of gel or something that is deformable, that this is going to break down. This is an assumption that will break down, and you'll have to change your physics to describe that breakdown of that assumption. But from here on out, we're going to go with this idea of a rigid object, okay? Now, in a previous lecture, we talked about the relative kinetic energy of objects that are moving with respect to their center of mass, and that could be like a vibrational or a rotational kinetic energy, where the objects that make up the, where the little point masses that make up the object are moving with respect to the center of mass. In today's lecture, I'm going to focus on the rotational kinetic energy. So let's assume that we have a rigid object that's rotating about an axis with some angular speed, okay? And as an example, I've got my kind of retro record over here, okay? This could definitely be modeled as a rigid object, and we know that for records, the rotation axis is about the very center of the record right here in the T, okay? Now, if you break your record up into little chunks, and I've indicated a couple of the chunks here on the record with these little white squares, then you've got a certain amount of mass of the object that's contained within that white square. Now, if you divide it evenly up, each one of those little squares will have the same amount of mass, and I'll call that m sub I. Now, as the record rotates, this little white chunk right here will be moving with a specific velocity with respect to the center of mass, which is at the center of the record, okay? And so, since it's going to have that velocity v sub I, that means that if we sum over all the chunks of the record, that we could find the total rotational kinetic energy of our record. Each ith mass will have a kinetic energy of Ki is equal to 1/2 mi vi squared, in other words. Now, if it's rotating with respect to the center of the record, we can measure the distance from the center of the record to the point in question for each one of our little chunks, this white square right here, okay? And you might think of that as the radius, right? So here, you're depending upon the distance from the center of the record to the point in terms of how fast it's going. Remember from rotational motion, we discussed the idea that if you have a rotation axis and it's moving at a uniform angular speed omega, that the velocity, the translational velocity of that point, would be equal to omega times r. So that the further away you are from the rotation axis, the faster the point is actually going. So for example, this white square here towards the top of the record is further away from the rotation axis than this square down here, which is near the bottom edge of the record. And that means that the one at the bottom edge is going faster than the one here at the top, okay? Because it's further away from that center. So we would write the velocity of the ith point, v sub I, as omega r sub I, okay? Sorry, I put the I in the wrong place. It should be after the r. Okay. Anyway, I'll fix that later. Now, if we were to sum and find the total rotational kinetic energy for the object, we would sum over all the k sub i's. So that would be the sum of, over the I, 1/2 mi vi squared for the whole object. And then we just covered how you can write vi as ri times omega. And so that means that our rotational kinetic energy would be the sum over all my I chunks of 1/2 mi ri squared times omega squared, if omega is constant, right? Now, what we can do is, omega is a constant. It doesn't change depending upon how far it is from the rotation axis or anything like that. So we can pull it out of the summation. And the 1/2, that would also pull out of the summation as it's a constant. And so we could pull the 1/2 and the omega squared out, and that would leave us with the things that do change, right? And that would be the sum over I of mi ri squared. Now this stuff in brackets right here is called the moment of inertia of the object, okay? And so we could then write the rotational kinetic energy as 1/2 times the moment of inertia of the object times its angular speed omega squared. So just to reiterate, the definition of the moment of inertia is I is equal to the sum over I of Ri squared times Mi. That means that the dimensions of the moment of the inertia are a mass times the length squared, which would be kilograms meters squared in SI units. Now, if you have an object that has a motion of the center of mass, which would be a translational kinetic energy, and a rotational kinetic energy, where it's rotating about the center of mass, like maybe a wheel rolling along the ground, for example, where the wheel is translating with respect to the ground, but of course in order to move it's also rotating. Then you could find the total kinetic energy using the sum of the translational plus the rotational kinetic energies. And that would be 1/2 mv squared plus 1/2 I omega squared, where big M here is the total mass of the object, v is the translational velocity with respect to the ground of the center of mass, I is the moment of inertia, and omega is the rotational speed. Now, of course, the units of rotational kinetic energy are joules, just like the units of all other kinetic energies are joules. Okay, so now we have our moment of inertia defined, assuming that we can break it into little chunks, okay? So let's say that we have, instead of something that's got a bunch of point masses, for example, an actual continuous object. Then how would we find the continuous, or the moment of inertia for a continuous object in a simple way? So what we could do is first look at our summation here. The moment of inertia I is the sum over all the little I chunks from 1 to n, say for example, of Ri squared times my little delta m. Delta m is the mass of each chunk, and Ri is the distance of each chunk from the axis of rotation. Okay, now, if I make my chunks smaller and smaller so that I break my object into tinier and tinier pieces, then what will happen is that in the limit as this delta m approaches small values, or 0, it'll become an integral of r squared dm rather than a summation over Ri squared delta mi. Okay, as an example, let's consider a rod, okay? So let's say that we have a rod and it's made of something like steel or something that has a nice uniform density everywhere. And what we do to find the moment of inertia for our rod is we break our rod mentally, that is, up into a bunch of little chunks. Here I have it broken up into 12 chunks, but it could be more than that, okay? Now, let's just say that the total length of our rod is going to be the number of chunks, big N, times the size of each chunk. And if you want a good calculation, you would make all your chunks the same length, so I'll just call that delta x. Okay, so each one of these little chunks here has a length to it, delta x. And since the rod is made out of a uniform material like steel, right, then if they have the same length and width and dimensions, then each one of these chunks would also have the same mass. We'll call it delta little m. Okay. Now, the length of the rod could be expressed, L, as the number of chunks, big N, times the length of each chunk, delta x. So let's say that we had, for example, a 12 centimeter long rod, and you broke it into chunks of 1 centimeter length apiece, then 12 times 1 centimeter is 12 centimeters, right? Now, if you have each one of these chunks having a small mass amount that's equal called delta m, then the total mass of the object could also be expressed as the number of chunks times the mass per chunk, or big N times delta n. So that means that we could find an expression for what my delta little m is, right? The mass of each chunk, or delta little m, could be expressed as the total mass of the object, big M, divided by the length of the object, big L, times delta x, the length per chunk. And I got this by solving for what n is in terms of L. If L is equal to big N times delta x, then n would be L over delta x, right? And then I just plugged into my equation here for big M equals big N times delta M and solved, okay? Now, let's look at this. We have our definition of the moment of inertia. is the sum over I, mi, ri squared. And as I said here in my example with the rod, each one of those mi's is the same mass, our little chunk size, delta m. And then what we're really saying, let's put our origin for the rotation, or our rotation axis, right in the middle of my rod here. Okay, so here's my coordinate system with this arrow. And the x-axis, let's say, is the one along which my rod is oriented. So the axis of my rod lies along the x-axis. Okay? So if I'm rotating about this axis right here in the middle of the rod, then the distance from my rotation axis would be the coordinate in x for each chunk. So I would have the mass of each chunk, delta m, times the x coordinate for each chunk squared, x sub I squared. Okay, now using my values for the delta m from the previous slide, delta m is equal to big M over big L times delta x. Okay? And then I multiply that times the x coordinate for the chunk squared. So I can pull big M and big L out of my summation because it's a constant. These are constants, right? So I can pull that out, and then I have the sum over all my chunks of delta x times the x coordinate for the chunk squared. Now, if I did it not in 12 chunks, but a bunch of little tiny chunks, then that summation could become an integral as my delta x goes small. And that integral would be m over L times the integral from one side of my rod to the other side of the rod. Remember, I'm in the middle, so if I put my origin here and the total length is L, then I would be integrating from minus L over 2 to plus L over 2 of the x coordinate squared times, now delta x goes to dx. Okay, so that's the integration that I would be performing. Okay, so let's actually perform that integration. The integral of x squared dx is 1/3 x cubed evaluated to the limits. So that would be 1/3 times m over L times x cubed evaluated from minus L over 2 to plus L over 2. So plugging in for that, I have 1/3 m over L times L cubed over 8 minus L cubed over 8. And that would give me 2L cubed over 8 inside the brackets. Okay? So that means that I would end up with 2/3 m over L, L cubed over 8, and simplifying that expression, it would be 1/12 mL squared. Okay? So that is the moment of inertia for this continuous rod about its center, and that's how you'd find that sort of thing. Okay, now the idea that I've used here is actually changing my variable in an integration from being over a mass, dm, to a spatial coordinate. Okay? And I did that by using the idea of a linear mass density, okay? So this means that you're doing a substitution or a change of variables, and we do that because we want to switch to integrating over the spatial coordinate rather than the mass. Now, depending on the geometry of the object, dm could be expressed in different ways. So what I just did was a rod, and this would also work, for example, for rods, chains, ropes, things like that. They could be expressed via a linear mass density, or, as I already showed, a mass per unit length, big M over big L. Now we're going to say that that could equal to, for example, in our previous example we talked about steel, that could be some constant amount, right? Because each chunk had the same mass. So if that's the case, then you can set big M over L equal to lambda, some constant, and you would have a constant mass per unit length. Now if you do it that way, then your delta M is equal to M over L times delta X. That would equal to lambda delta X, because lambda is that constant value. And then if I took my summation over to an integral, I could express that as dm is equal to lambda dx. And then see, I'm integrating over my linear coordinate and not mass. Okay? Now, if you do it this way, you're just going to be doing a one-dimensional integral. In other words, you're only going to be integrating over one spatial coordinate. But that's not always the case. Sometimes you have more complicated problems. So, for example, we talked about records earlier. Now, that's a perfect example for a surface mass density. Disks or planar objects, those are better expressed in terms of their mass per unit area. In other words, for my record, I would have a chunk out of my record, and it would be pretty thin, so I could ignore its thickness maybe, but I couldn't ignore its area in spatial extent. And so in that case, I might take the mass and divide it by the area of the object, and that would give me a certain mass per unit area. Now these are often expressed by the Greek letter sigma in a lot of textbooks. Okay? So that means that my delta M would be my mass per unit area times my little area of my chunk, delta A. And that would be expressed as sigma times delta A. And then if I did that in terms of an integral, shrinking my dm down, or shrinking my delta M down to a dm, then I would write it as sigma times dA. Now, this could get more complicated depending on what coordinate system you choose. If you have spherical coordinates or cylindrical coordinates, it might not be this straightforward. But for example, in the Cartesian coordinate system, dA might be, for example, dx times dy, or dx times dz, or dy times dz. And in that case, then you're having to integrate over both those spatial coordinates. And so you've got a double integral, okay? Now, any object that's not easily expressed as a surface mass density or a linear mass density must be expressed in terms of a volume mass density, okay? And this could be something for an extended simple shape, like a cylinder or a sphere, or it could be some crazy object with some funky shape, okay? Now, in that case, you would have a mass per unit volume, which we would express as big M over big V. And then oftentimes that's expressed in terms of the Greek letter rho, okay? I already talked about steel, copper. Solid materials like that, for example, do have constant volume mass densities that you can look up in tables, okay? So for example, if you're writing it this way in terms of the mass per unit volume, then your delta M would be your mass divided by your volume times the size of your chunk's volume, which would be delta V. And then if M over V is some constant value, you could set that equal to the density rho times the chunk volume, delta V. Now, if you're taking it to an integration instead of summation, that would mean that dm is equal to rho dv. Now, in the Cartesian coordinate system, your dv would be dx times dy times dz. And in that case, you're doing a triple integral. Now, in a lot of problems in real-world situations, you're going to have that constant mass density. So, for example, I talked about steel and copper, and those have constant mass densities. Like the density of copper is 8.9 grams per cubic centimeter, roughly, and that's a constant. So if I had a solid object made of just copper, then I could be relatively confident that my volume mass density would be the same everywhere, so that if I took a little chunk of, say, 1 centimeter cubed, that it would be 8.9 grams, regardless of which chunk I took. But it's also true that real objects are usually made of different kinds of materials stuck together, right? And in that case, the density of the object would not be uniform. It wouldn't be a constant value. If that is the case, you need to include how the mass density depends on the position within the object. Sometimes in introductory level problems, for example, they might have a simple expression saying that, for example, the density of a sphere varies with its radius or something like that. And then you would sum or integrate considering that variation. Okay, well, that's my introduction to the definition of moment's inertia and mass densities. In the next lecture, I'll go through how to find the mass densities for certain objects and give you some examples. Let me know if you have any questions, and I'll see you in class.